All right, so the last thing I want to do is to make a better implementation of counters. So ints are really, there's a type of arbitrary size numbers built in, but ints are really 32 or 64-bit machine words, which means that there's a maximum number around 4 billion or for 32 bits or more for that. Okay, so like ints only go up so far. So if you wanted to do a calculation that involved bigger numbers than that, than 32 or 64 bits, then you would need a type of numbers that can represent counts bigger than 2 to the 32 or 2 to the 64, or because they're signed, it's actually like 2 to the 31 or 2 to the 63, because you still have them for negatives. So we can make another implementation that, suppose this didn't already exist in your programming language, we didn't have a library for this, we can make another implementation of counters where instead of representing a counter by a machine integer, which has a fixed size, just like floating point numbers have a fixed size, we represent counters by int lists. Okay, and so the idea is that we're going to explicitly represent the bit structure. And int here is a little bit of overkill because really we only need 2 possibilities, so we could compress this, but let's just use ints for simplicity. So the idea is that, for example, if you have the list C0, C1, C2, C3, dot, 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 okay, what that represents is the coefficients of representing a number in binary, which means you have C0, let's write it without the underscores, times 2 to the 0 plus C1 times 2 to the 1 plus C2 times 2 squared plus C3 times 2 cubed plus, and so on. Okay, so for example, if I've got the list 1 that represents what? The number 1, because 2 to the 0 is 1. If I've got the list 0, 1 that represents 2, because it's 0 1s plus 1 2 is 2. If I've got the list 1 1 that represents 3, because it's 1 1 and 1 2, which added together is 3. If I've got 0 0 1, that represents 4, because it's 0 1 0 2s 1 4. If I've got 1 0 1, that represents 5, and so on. Okay, so the idea is that we're going to represent our counter by lists of bits explicitly so that we can do that. And so now what we have to do is to go through all the operations in our counter signature and implement them for this implementation. So for example, what is 0 in this representation? It's the empty list. And in fact, I could have used any list with all zeros in it, but maybe let's say we're going to have the invariant that there's no trailing zeros there. Oh, and I should say that this is sometimes called a, well, I forget the name, but key point to note is that the lowest order bit is at the front of the list, right? You could instead have represented this by the same list flipped around in the order. I think this is called lower endian representation. Okay, so now what we need to do is to figure out how to increment a list of bits. right? So if you give me a counter, I have to give you a new counter that represents adding 1 to it. But now our counter is not a number, it's a list of numbers. So we can say case L of, if it's empty, something, or if it's x times x's, then something else. All right, so if L is empty, that means it represented 0. If it represented 0 and we want to add 1 to it, then we get 1. If L is not empty, then because we're working with lists of bits, we actually know, that it's going to be either a 0 or a 1 at the front. And if the first bit, which is the lowest bit, that is the coefficient of 1, 2 to the 0 or 1, is 0, then to add 1, we just change it to a 1. On the other hand, if it's not, we want to put a 0 at the front, but then, right, which is changing the last bit to a 0, but then we need to carry the 1, which we can do by incrementing x's recursively. Okay, and so if we load this, it'll say, okay, you're doing good, except there's no show. So the last thing we need to do is to write a show function, which takes a counter and returns a string. And to do this, we're actually going to need a helper function, because what we'll need to do is keep track of the coefficient of 2 that we're on so that we can print it out. So, okay. I is the power of 2 for the first bit in the list is the idea here. Okay, so if L is empty, then I don't know, let's just print that as 0 or something. On the other hand, if L is x times x's, then the idea is that we've got b powers of 2 to the I plus show help of I plus 1 and x's. Okay, and then if we finish this to do show, we're going to do show help, and the list will be L. And what power of 2 does L starts with? It starts with the 0th power of 2. Okay, so let's see if that loaded. Where did I forget a caret? No, B is in scope. Oh, sorry, the bit there is called X, not B. Cool, okay. So now, just to get an example of what's going on here, for example, using this, I can say bin counter dot 0, and that's the empty list, and I can say bin counter dot increment of bin counter dot 0, and that's the list 1, and then I can increment that again, and I get the list 0, 1, and I can increment that again, and I get 1, 1, and I can increment that again, and I get that, and I can increment that one more time, and I get 5. Okay, good. So that seems to be working okay. Our increment's working okay. And so now if I do bin counter dot show of all of that, then I get some printout. And so what does it print as? It says 1, 1, 0, 2s, 1, 4, and then plus 0 from the empty list there, just to make the printing work out nicely. And we're there. Okay. What I can't say is bin counter dot show help of 0 and that. Variable, unbound variable or constructor show help in path bin counter dot show help. Okay, so why is that? Well, there is a function bin counter dot show help, but hey, we said bin counter is an implementation of this signature counter, and the signature counter says that there is a counter type and a 0 in increment and a show, and that's it. And so you're not allowed to refer to anything else in the structure that's not in the signature. The client code also doesn't see any functions, types, values, that are not in the signature. Okay, and the reason that this is the desired behavior is that the idea is that like this helper function that I wrote that takes a counter variable, like takes a loop increment counter variable I, is not something that I'm intending to be exposed to be used by the client. I might, decide that I'm going to do show differently and then revise this so that there is no show help anymore. Like that's my private business in the counter, the show help. Nobody else is supposed to see it, and the module system prevents you from referring to it. It says, well, if you said that counter provides 0 increment show, then hey, you don't even know that this show help exists. So that's keeping that private there. So you can call a show, but you can't call a show help. Okay, and so now um, that's an example of how that works. And then as an example of implementation evolution, changing the implementation uh, without, sorry, as an example of client evolution, changing the client without changing the implementation, because we've said that our count evens works for any counter implementation by only referring to the things that are in the counter signature here, we can yeah, okay. Replace int counter with bin counter everywhere where we used it, right? So we're just replacing, hey, I don't want to use those int counters anymore. We'll see a better way to do this in a couple lectures, but if I just go through and replace my int counters with bin counters everywhere and reload it, then now I can do my show evens on some list, and without changing anything about the client code except for which module it refers to, suddenly the client code is now using all of those functions from the bin counter module instead of the functions from the int counter module. And so what we get is the bin counter answer here, right? So if I count the number of evens in 5 twos, I get 1 plus 4 is 5, good. And so I've changed the code to refer to the bin counter. And if we wanted to make this a little easier to switch back and forth, I could say structure C equals bin counter, just to give another name to it, and then just say C dot everywhere. And so then I can do that. And then if I change C to be a reference to the int counter implementation, then it does things with int counters instead. So what we've got there is the idea that the implementation can refer to sort of works for any, the client works for any implementation of the signature. And so you can switch back and forth between them. Okay, so what we've seen is a first example of dividing the program up into chunks, modules, structures, right? I've got my implementation of the counter over here. I've got my client code over here. The chunks that interact were limited in the sense, well, we didn't really see that yet. But for chunks that do interact, we specified their interactions with the counter signature, and that said counters consist of this, that, and the other thing, and all the client can use is this, that, and the other thing. And so we've got this picture where the interface is sitting in between the implementation and the client. And so the idea is that, to come back to it being easier to understand, well, if somebody handed you this and said, maybe a little bit more about it in a comment, like this represents the zero counter and this adds one to the counter and this does the counter to string, then you could write this code without really understanding all of the details of this junk for representing counters as lists of bits and printing them out in some funny way and stuff like that. You, the programmer who's using this API, don't need to think about all of that stuff. All you need to know is what's in the signature here. And we've seen that we can evolve the implementation, involve the client by changing implementations without actually editing the implementations themselves, right? We just make a reference to a different implementation. We haven't really seen the last two yet. We'll get to that later in the week or next week. Okay, so that's the end of the introduction to modules. In lab, you'll do some more examples of signatures and structures.